Hello, Mr. Aaron, Mr. Ryan, alright?
Mm-hmm.
Last few lessons we talk about the maze problem, right? Maze. So basically we want to find out the nearest exit to the entrance in the maze. Okay? And the entrance could be anywhere actually. It doesn't actually have to be on the border, but let's to simplify, the entrance is the empty cell on the border. And the exits are empty cells on the border. Right? The empty cells. For example, these two, okay? So obviously the entrance is not the exit. If we put the people here, little people here, and we can't go back to where the same entrance, right? It's not counted as an exit. We talk about the breadth search, and we talk about the depth search, right? So these two are the popular path finding algorithm in a graph. We want to find out the shortest path in this unweighted graph. Unweighted because each step, right? So if we are here, so we have 4 directions to go, and each time we move one position, it costs 1 step. This is unweighted, okay?
Yeah.
It has to be unweighted because if it's weighted, then breadth search and depth search is not working, right? It has to be unweighted. So breadth search level by level, we use the DQ level by level. This breadth search algorithm guarantees that as soon as we find the exit, it's the shortest, right? So for example, like in this graph, it could be 2 exits, right? It could be 1 exit here, 1 exit here. But if we perform the breadth search level by level, this axis is the shortest, but not the depth search. Depth search, we perform the depth search, we go as deep as we can. And then the first exit we find is this one. This one is clearly not the ultimate. The ultimate is this one, right? Okay? But we can apply the depth search to find the shortest path if we explore all the paths, right? If we just brute force the graph. And then we know there are 2 axes, then obviously we know this one is the shortest, it's the ultimate. Breadth search queue, DQ, first in, first out. We push the node into the queue, and then we take it out from the left hand side. That's the top left. And then we push its next step back to the queue. This is in queue. When we push the kids back to the queue, we have to make sure this node is not visited before. So we use the hash set. Or alternatively, we can mark the visited cell walls, right? Okay? So look, because each cell, we can only visit it once. So as long as we put it into the queue, we can mark it as a wall, right? So it's not pick up again. And for the depth search, the same thing, okay? But for depth search, we have to mark and unmark. Yeah, we talk about this problem, right? Look, if this is exit, then here is exit. Wall. For the depth search, it could be somewhere here, right? Here. Right? We found a path. But this is not optimum. This is optimum, right? But if we're not unmarking this pixel, so this pixel is taken, so obviously we can't go through this path again.
Can't even do a second one.
Yeah, and that's why we do this depth search. We have to unmark it, mark and unmark it, and we use the recursion, right? We talked about that last lesson, right? Okay, so Ryan, you said this lesson we're going to talk about what kind of algorithm?
Iterative deepening search.
Yeah, we're done. Iterative deepening search. Okay, iterative deepening search. It's simple, but to do this iterative deepening search, we have to find out how do we do this depth limit search. Okay, limit search. What's depth limit search? It's actually depth first search, but with the limit, right? With the limit. DFS, so depth limit search is actually depth first search plus limit, with limit, okay? Look at this tree, yeah, binary tree, or it doesn't have to be binary tree. Actually, it's a quote tree, right? What's quote? QUAD means 4, right? Why is it 4? Each cell at most has 4 kids, right? You can move to the neighboring 4 kids, so it could be 4 kids. Is this means 4 in English?
Quad, yeah.
Yeah, quad means 4, right? Quad tree.
It's just like bi means 2.
Yeah, quad tree.
And try means 3.
Yeah, this is binary tree, quad tree actually. With the limit, what's the with the limit? At the beginning, we set the limit to 0, okay? So when we set the limit to 0, we had a hard limit at here. So if this is not the axis, we stop. We increment the limit to 1. Okay, so when we increment the limit to 1, so basically we're seeing this simplified quote tree. So we perform a depth search. We don't find it. We increment the limit. Okay, so we perform a depth search. Look, and then found the exit, right? And then this is the shortest.
Why are some of them red?
Good question. Red means that this is the exit. Sequence. What's our sequence to finding the exit? The iterative deepening search.
That's because the red pen has been on some
Okay.
black pen and red and
Red mixed with the black. Okay.
yeah, and it looks like brown.
Okay. Let's do the breadth search first. Breadth search order.
So easy. 1, 2, 3, 4, 5, 6, 7, 8.
Hey, okay, we found it. This is the
So
shortest.
easy.
This is the shortest. Okay, what's the depth search order?
1, 2.
If we go to the left first, you know the depth search have different order. If we visit the node left right, okay, we visit the node and then left and right. This order. This is called pre-order, right?
4, 12,
13.
5, 6, 9,
Okay, we find this. This is not the optimum, right? So we need to continue.
3, 7, 10, 11, 8.
Okay, and then we found this, and this is the optimum. Okay, what's the iterative deepening search? We set the depth to 0. What's the order now? 1, right?
Yeah.
It sees the limit. Basically, when I set that to 0, it means that we only see this tree. We only see this tree. Okay? This is 1, okay? We don't find it. We increment. We need to. Come on, listen. We increment the depth to 1. So what do we see? Here. What's the depth search? 1, 2, 3. We don't find it, okay? We increment. Okay, what's the depth search?
1, 2, 4, 5, 6, 3, 7, 8.
Got it. Okay, we find it, yeah? At the beginning, d equals 0, right? This is the recurrent limit. So the maximum d, given this maze, this is the columns C, and this is R. Can you imagine what's the longest, what's in theory, what's the longest path for entering to the exit? What's the longest? It's just given a rough number. I mean, rough, if this is R, this is C. What's the longest? You can imagine. The longest, I'm not talking about shortest, longest. So in what cases you can get the longest?
You never go to the exit. Or
There's an exit. What's the exit
you
longest?
just loop.
Loop?
Yeah, you loop.
No, you can't loop. That's actually a very good point. Okay, if we can loop, there is no longest, right? You can just go round and round. Okay, how about you can loop?
A very long maze from top left to bottom left.
That's right. Yeah, it could be the entrance is here, right? The exit could be here. It could be like that, right? Okay, this is longest, right? So that's R times C, right? R times C. In theory, right? In theory, okay? So while D is smaller than, because it starts with 0, smaller than D, right? Then if we perform this step limit search with current D and then entering, yeah, the entering. And then obviously we need to have a hash set or marking the position, visited position, walls, and unmark it, okay? Let's use the hash set first. Scene table, so we put a set, hash set, a notebook, right? If we find it, then return D, right? Okay, so one question, can you tell me why if we find a node and it guarantees the shortest? So how do you prove it's the shortest if we...
I just visually look at it.
Yeah, I know. I mean the depth limit search. Why we do this iterative deepening search? You know,
because you can go like level by level. You're basically
yeah, basically go level by level.
Basically like
Breadth
search, but traveling by depth search.
That's very good. That's actually what it is. Okay, so return D. Otherwise, D plus equal 1. Right? And if we can't find it, return minus 1. Right? The point is this depth limit search with the D. So this is quite similar to depth search, and we just have to add one more criteria. When we hit the limit, and then we stop, right? That's the difference, right? Define depth limit search D, the entering, right? The current position, okay, position, and scene table. If the position is exit, okay, I'm writing the pseudocode, and also position is not entering. Then we find it, right? We find the exit, then return true. Okay, and then if this position already seen before, return false. We don't go back. Otherwise, the first thing is to put it in a notebook, right? And then we have to check. Look, if D is smaller than 0, right? It's more or equal than 0, then return false. Right? Basically, we are exceeding the limit, the depth limit, right? And otherwise, you know what to do, right? For DRDC, in 4 direction, right? In 4 direction. In the neighbors, in 4 direction. 1 0 0 1 1 0 0 1. This is the direction of set, okay? 4 direction. 0 minus 1 minus 1 0. And then NR NC equals the DR plus R DC plus C. Okay, RC is actually from position. RC equals position. Okay, and then if we need to check NR is with the range, rows, and NC is also with the range, and also if the maze NR NC it's not a wall, right? It's not a wall. We don't go to the wall, right? If it's a wall, we don't go in there. There's no point. We can't pass through the wall. If depth limit search, that recursion, this is basically recursion. With the d minus 1, right? With the d minus 1. Depth of search, this d is incrementing. And the depth limit search, we can do it opposite, which is decrementing. We decrement the positive d. Because here is passing the positive d. We decrement it until it falls below 0 or below or equal 0, okay? And then return true, right? The position, NRNC, the scene table, and then return false. Okay, so look, here we edit, so we have to unmark it. Remove, right? Remove RC. Okay. Look, this is pretty much like a depth search. The only difference is this one. Look, this one. Yeah, what's this? If d is smaller or equal than 0, return false. What's this mean? Why are we adding this criteria? One question.
Because it's
What's
because you're doing like level by level thing.
Yeah, basically, we perform the depth limit search, right? If we set the limit to here, then we don't go to the deeper one. We leave it to the future, right? This is what it means, yeah. All the rest similar to depth search. Okay, so this actually guarantees the shortest path, right? And then it's more efficient than depth search, obviously, but it's not as efficient as breadth search, right? But why do we need this iterative deepening search? Depth search, right? This is not a good player here, right? This is not optimum. But how about iterative deepening search versus the breadth search? Right? This is guaranteed the shortest path. This guarantees shortest path. So why do we need to use the iterative deepening search, and why do we need to use breadth search in some cases? Okay, so these two both are okay, but breadth search, because we have a queue, right? We have a queue. So this has this larger space use, right? The iterative deepening search is basically, recursion. So it has a O. Look, when you set the hard limit to D, right? It has an OD space uses, right? Because look, you only store current path, which is 3 node, right? Yeah, 3 node. The depth search, right? Depth search. You visit this. You only store the path. The space uses, you only store this path, right? But for the breadth search, you need to store all the nodes in the current level, which could be very big. So the space uses, in terms of space uses, this is efficient than breadth search. Iterative deepening search is also has the same space uses in the depth search, yeah? Depth search. Okay. So what have you learned today?
About maze.
I
We do need iterative deepening search.
Okay, so more details, please. Eric, you go first.
Okay, so I learned about iterative deepening search for a maze.
Yeah.
And so basically, breadth search, and you have a limit for your depth, and then you search for the exit, and then if there's no exit, you increase the limit one step further, and then so on until you get find the exit, and which is the shortest exit. And also, I learned iterating deepening search is more like use. It has less use of space than breadth search, as it just breadth search just chucks the nodes in the queue, and while iterating deepening search just only uses only one path.
Yeah, well done. Good job. Okay.
About maze.
maze, finding the nearest exit to the entry in the maze. We have so far covered 3 algorithms: depth search, breadth search, iterative deepening search. Okay, so these 3 are the path finding in the graph, right? Basically, we can visualize it in the graph: binary tree, trie tree, chord tree, a graph, and directed graph, weighted and unweighted graph. It has to be unweighted, okay? Because if it's weighted, then we can't apply the breadth search. We have to use the Dijkstra. Remember we talked about the shortest path, Dijkstra. Floria, yeah, Floria Washa, yeah. Dijkstra. D-I-K-J, Dijkstra, we talk about that. Floria Washa. Okay? And uniform cost search, yeah, we talked about that in about 100 days, 200 days ago. Uniform cost search, okay? Yeah. Okay, that's it for today. Bye-bye. Bye.